Happy Wednesday. So we are in week 13 right now, which we're still working on probability this week, combinations, permutations, and I threw up this problem that I found on the internet, kind of been sweeping the internet right here. And if you would like to pause the recording and check it out, you can do that. But it looks as if there's no answer, like that not enough information is given, but in actuality you really can figure out Cheryl's birthday just by Albert saying, I don't know when Cheryl's birthday is, but I know that Bernard does not know too. That's crucial information right here. So just from this first clue, we're actually able to cross off, I think, 5 dates up there. You're like, what? Cross off 5 dates. So if you want to look this up later when you get home, this is the Singapore math problem, and it's all over the internet right now, and there'll be video explanations or typed explanations if you want to find out when Cheryl's birthday is. I did that this morning. I figured this out this morning. So for week 13, your essential question, this week I'm not giving it to you at the beginning or at the end, but instead it will be somewhere in the middle of our session. That's just to make sure that everybody is staying on track, paying attention, taking really good notes. So today we're jumping into probability. So let's talk about dice for a second. Picture a dice. I put a picture of one up here for you. How many sides does a dice have? Everybody says 6. What numbers are on the dice? 1 through 6. Does any number appear twice? No. So each number only appears one time. So when we're talking probability today, anytime I say probability, we are going to represent that with a capital P. Can you write that on your notes next to the word probability? So if what I'm asking you for is probability, probability is represented as a fraction. So it says it's n of e over n of s. So what does that really mean? What do we want to have happen over how many possibilities do we have? So whenever we're making our fraction, the top is what we want to have happen. So for instance, if I come down over here, the probability of rolling a 5. What do I want to have happen? I want to roll a 5. How many 5s are there on a dice? 1. Perfect. So the 1's going to go on top because that's my desired outcome. That's kind of what they call it. Then on the bottom of my fraction, it's how many total options you have. So when you roll a dice, how many total options do you guys have? 6. Fabulous. So our probability of rolling a 5 is 1 out of 6, which we've heard it said that way quite a few times probably. But we're going to write it as a fraction. The other way you could write it is 1 colon 6. That means the same thing. So does anybody have a question about that first part? Probability of rolling a 5. The top is our desired outcome. What did we want to have happen? Roll a 5. How many of those are there? 1. The bottom's your total. So next it says the probability of rolling at least a 4. So how many desired outcomes would that be? Well, if I rolled a 4, I would be happy. What else would I be happy with? What else is at least a 4? A 5. What else is at least a 4? 6. So how many possible outcomes would I want to have happen? 3. And the bottom is always your total. What's my total? Still a 6. So now we're going to simplify. Exactly. So to start off, we're always going to do desired over entire, desired over entire, then we're going to reduce. So what this is really saying, you guys, let's kind of think about what probability means. This means 1 out of every 6 rolls, I should get a 5. 1 out of every 6 rolls, I should get a 5. 1 out of every 2 rolls, I would get at least a 4, meaning a 4, a 5, or a 6. So that's how we use probability. It's telling us our odds. Does that mean that's going to happen every time? No, but more likely than not. Probability means it's probably going to happen. See how the words are the same? It's what's probably going to happen. What about the probability of getting a prime? So let's think about out of 1 through 6, which numbers are prime numbers? 1 is a prime. What else is a prime number? 3. What else is a prime number? 5. We missed one. 2. So prime numbers are anything that's just 1 times itself. Everybody okay with that idea? So let's write my probability now. What is my desired outcome? How many different options do I have? 4. Out of what's my total? 6. So every 4 out of 6 rolls, I would get a prime number. Let's reduce. That would be 2/3. So every 2 out of 3 rolls, I would get a prime number. Kind of cool. So only 4 and 6 were not included as prime numbers. Does anybody have questions on my first slide? So if we're talking probability, we're going to have our P, our desired out of our entire. Desired, entire. Okay, so now we get to fill in our chart. So in your notes, hopefully you have them pre-printed, or if you're in person, I give them to you. We're going to do the probability of a sum being 6. What does sum mean? Sum means to add them, right? Everybody nodding? Sum means to add. So here's what I'd like you to do. Take this chart, which I gave you in your notes, and I would like you to put an X in every box that gives us a sum of 6. So what plus what would give you a 6? Can you put an X in all of the boxes where we would get a sum of 6? So take a couple seconds to do that. Everyone in the room have a copy of the note kit? Okay, how are we doing? We have our boxes in there. We have our X's. Did you guys notice a pattern about your X's?
Yes, they go diagonally.
They do. They go in a diagonal. So my 1 and my 5, 2 and 4, 3 and 3, 4 and 2, 5 and 1. So when we're talking probability, again, it's a fraction. My desired on top, entire on the bottom. So how many options do I have for getting a sum of 6? How many X's do you guys have? Okay, so there are 5 options of getting a sum of 6. What's my entire options, though? Think about it for a second. So 1, 2, 3, 4, 5. There's 5 different ways for me to get a sum of 6, but what are all of my different options? What do you guys think? 36. So it was 6 times 6. Everybody okay with that? So picture what's going on here. You're given 2 dice, and I should have brought my dice over today. You're given 2 dice in your hands, and you're rolling 2 dice. This is finding the probability that the 2 dice that you roll have a sum of 6. So 5 out of every 36 rolls are going to give you a sum of 6. We're going to try and state this a different way. Mr. Brummer needs to know all about probability. Just ask him. He's really good with probability stuff. Let's try again. So I have a new chart for you. This time I want the probability of having a product that's 30. So use the chart the same way. Can you guys make X's in the chart anywhere you would get a product of 30? So first we need to recognize our math vocabulary, right? What does product mean? Multiply. So I need to mark the 2 spots. I gave you the answer. We need to mark the spots where I get a product of 30. So 5 times 6 and 6 times 5. Are there any other spots where you'd multiply the 2 and get 30? No. So how do I write my fraction? My desired goes on top. So how many boxes are what I would want to get? 2 out of my entire. How many total options do I have? 36. So what's my probability when you reduce it? 1 out of 18. So this means if you guys were to roll the dice 18 times, only once would you get a product of 30 on your dice. Does that mean that's going to happen every time? No, that's just the probability, meaning it's probably going to happen. Everybody okay with that idea? Somebody, have you guys heard of lucky sevens in Vegas? Like people who are just on a hot streak and they keep rolling 7 after 7 after 7. Are they always going to do that? No, but you could figure out the probability of them being able to do that. Good job. So again, what this is saying is that 1 out of every 18 rolls would give us a product of 30. How are we doing with probability so far? So far so good? Questions, comments, concerns? Okay, great. So now think about this one. What's the probability of an event being 0? Remember how on the last slide my probability was 1 out of 18, right? 1 out of every 18 rolls, I'm going to get a product of 30. What kind of event would have a probability of 0? Well, that's only going to happen if it's impossible for an event to occur. So let me give you one. Oh, it's right here. If we roll a 6-sided dice, what's the probability of rolling a 7? If you roll 1 dice, could you ever get a 7? No. So your probability would be 0. See what they're saying? Sometimes it's not possible. What about my probability of getting a 1? Well, that's only going to happen if it's absolutely certain the event will occur. For instance, if we roll a 6-sided dice, what is the probability of rolling at least a 1? 100%, right? 100% certain it's going to be a 1 or higher. So sometimes we are going to have a probability of 0 if it's never going to happen, or you'll have a probability of 1 if it's always going to happen. Everybody okay with that? If I only put red marbles in a bag and I hand it to you, what's the probability of you picking a red? 100%. It's going to happen. It's the only thing in the bag. So sometimes it's 0, sometimes it's 1. I just wanted to make sure you guys understood that we do have real life examples that have those types of probabilities. Okay, so now we're going to combine what we did last week with this week. And this is kind of a funny story because I have a 4-year-old. He doesn't know how to spell yet, but he actually knows what the starting letter is. He just doesn't know how to finish the words. He's in preschool. So pretend I give my son Ethan the letters P, R, C, and O. You know those magnets that you guys used to have as kids, like rearranging them on the fridge and stuff? I want to know, he's randomly arranging these 4 different letters. What's the probability? Oh, it says her. We'll pretend we're talking to my son here. What's the probability that he arranges them to form the word crop? So we're going to combine what we did last week. So here's my question to you. Is this a permutation or a combination? One of them, order matters. The other one, order didn't matter. Remember last week, that was part of our essential question? First, let's say order matters. I need them to spell the word crop. That's my whole question, right? So order matters. Which one of these 2 words means that order matters? Do you remember? Permutation. So can you circle that on your notes, please? We're talking about a permutation because our order matters. Let's write that in there too. Order matters. So order matters, we're trying to spell a correct word. So now let's remind ourselves of what our permutation formula was. Permutation formula, you can add it sort of to the side of this slide or right underneath this slide. I left some blank space for you guys. It's n factorial divided by n minus r factorial. That's our permutation formula. Okay. So now we're talking probability. We're combining probability with permutation. So everybody do a capital P for me over here. So the probability of forming the word crop. So everybody so far so good? We're doing the probability of forming the word crop. On top is how many ways do we have to spell it correctly? 1. Good job. Right? The top is my desired outcome. How many desired outcomes do I have? Only 1. Has to be spelled in the right order, the right way, only 1. The bottom are what are my entire options. Everybody still with me? Desired over entire. How do I do my entire options with using a P, R, C, and O permutation formula? So this one's going to belong on the bottom. We're going to do n factorial divided by n minus r factorial. So here we go. I'm going to just switch colors, that way it stands out. So what's my n? How many total, or how many am I choosing at a time? Or actually, here, 4p4. How many total? How many are you choosing at one time? Remember from last week now? And it's been a couple days. So how many total? How many are we choosing at a time? 4 letters total, and I'm going to use all 4 letters at one time. So my n is 4. And then my n minus r would be 4 minus 4 factorial. So we did the whole bottom chunk last week. This week we're just adding it into probability now. So on top I'm going to have a 1. On the bottom I'm going to have 4 factorial divided by, what's 4 minus 4? 0. But what did we learn about 0 factorial last week? You guys remember?
1.
0 factorial is 1. So I'm not even going to write it. So I really have 1 divided by 4 factorial. So I have 1 divided by 4 times 3 times 2 times 1. So 12 times 2, 24. So if my toddler is randomly arranging the letters P, R, C, and O, 1 out of every 24 tries, he's going to get the letters in the right order. Kind of cool. Any questions about this one? We're going to try again, combining probability with permutations. Okay, next problem. So events, again, that are permutations or combinations. So Rochelle randomly pulls out 2 cards from a standard deck. What's the probability of getting a pair of aces? So this time we have to ask ourselves, does order matter or does order not matter? Order does not matter. I don't care if the ace of diamonds comes before the ace of spades. Or I don't care if the ace of clubs comes out and then, what's the other one? Hearts. And then the ace of hearts. Order doesn't matter. I just care that they're an ace. So if order doesn't matter, am I talking permutation or combination? Combination. Great. Let's circle that one. Do we remember that my combination formula is very similar to permutation except for one change? Let's write it up here next to the slide. It's n factorial divided by n minus r factorial. So far that's all the same, right? It's the same. Who remembers the last piece of the puzzle that's different for combinations? Missing one thing. Another r factorial. So let's try together. I want to do the probability of picking 2 aces. So let's write it this way. Notice that when I do my P, inside the parentheses, I like to tell what I'm talking about. I'm talking about the probability of picking 2 aces. So this time, I need to know how many ways are there to pick 2 aces, picking 2 at a time, divided by the ways to combine 52 cards 2 at a time. So now that we're talking about cards, let's take a step back real fast. How many different cards are there in a deck? Do we know how many total in a deck?
52.
Okay, 52. Can we make these notes somewhere because we're going to need this today? So 52 cards in one deck. How many different suits are there? Do you guys know what suits are? Like your clubs, your diamonds, your hearts, your spades. So 4 suits. Let's put what they are in parentheses. I have hearts, clubs, diamonds, and spades. Because sometimes they'll give you guys questions, but you know, like I'm quite a bit older than you. Knock on wood, I know I am. But we used to grow up playing cards. And you guys probably don't do that as much as what we used to do. So maybe you're not as familiar with cards. How many cards are in each suit then? So if there's 52 total and there's 4 suits, how many of each kind are there? There are 13. So 13 of each type. So there would be 13 diamonds, 13 hearts, etc., etc. I'm just going to go dot, dot, dot. Those are kind of the 4 biggies that you need to know when we start working with questions about cards. Okay, so I'm going to go back now to our problem here. Because order doesn't matter, I'm using combinations. So I'm going to talk about what's my desired outcome on top. My desired outcome is to pick 2 aces. Over my entire outcome belongs on the bottom. So how we do that, it's going to be 4 total cards, picking 2 at a time. Think about why that's my desired outcome. How many ways are there to combine 4 aces, picking 2 at a time? That's my desired outcome, 2 out of the 4 aces. My bottom is my entire. How many entire cards are we talking about? 52. So out of 52, C. And still, how many are we choosing at a time? 2. Good job. So let's pause real fast and recover what we just did. So the top is my desired outcome. My desired outcome has to do with the aces. How many aces are we talking about? 4 total, but I'm only going to pick 2. On the bottom is your entire. What's the entire deck of cards? 52. How many am I picking at a time? Still just 2. So from here, I have to plug in my numbers into our formula. So the top is going to be a fraction. This bottom is going to be a fraction. I'm going to switch colors so we can see it a little bit easier. The math itself is not tricky math. Like you guys saw, it's just like multiplying the factorials out. It's really just setting up the problem. So on top we will have 4 factorial over 2 factorial, 2 factorial. I should say 4 minus 2 factorial, if we're going to write it all out. And then on the bottom, we get 52 factorial divided by 52 minus 2 factorial times 2 factorial. And we practiced working these out last week, so please don't see 52 factorial and think, oh my goodness, I have to go 52 times 51 times 50 times 49. We don't have to do that, right? We learned a trick about the top and the bottom. Once they match, you can cross them off. I will just do the bottom real fast just to remind you, and then I'll give you the final answer so that way you can review it later. So on top, I'd have to say 52 times 51 times 50 factorial. On the bottom right here, I get 50 factorial, 2 factorial. So see how those are going to cancel? You're left with a really nice, neat problem, which you are allowed to use a calculator to say 52 times 51 divided by 2. So on the bottom, you'd end up with 1326. So if here's your total bottom fraction, 1326. And on the top, you'd end up with 6. So it reduces to 1 over 221. So I'll give you time to practice that a little bit later. The key really is just setting up the problem and then doing like we did last week. So does anybody have a question about the bottom? 52, 51, 50. My 50's been canceled, so they just go away. So I was left with 52 times 51 divided by 2, really. Okay, so the last 2 problems covered. One where it was a permutation because the word crop, my order mattered. So I'm using my permutation formula. The second one, I was just combining 2 aces. So that's my combination formula. So just remember, that's the biggie. You have to be able to pick out, does order matter or does order not matter? Because it tells you what formula to use. So now we get into one new idea, which is with and without replacement. And it's just like it sounds. So with replacement would be something like this. Don't read down here yet. So with replacement is, here's a bag of marbles. What's the probability of you picking out a blue? Okay, you pick out a blue. You put it back in. That's replacing it back in the bag. Now what's the probability of you picking a blue again? And you pick out a new marble. So with replacement means after each pull, you're putting it back in and starting with the whole thing again. So you pick one out, you put it back in, shake it up. Pick one out, put it back in, shake it up. You're replacing it back into the pot of the whole. Without replacement is you pick a marble out, you got a blue, yay, set it to the side. Now what's the probability of picking out a blue with what you have left? Now what's the probability of picking it out with what you have left? So without replacement, it means you're not putting it back in the bag. You're going to have less and less to pick from each time. So use the words to help us. They have special formatting for how they're going to write it, which is not a huge deal. I'll teach you how to use this in a minute. So if there is replacement, all that means is you're going to do the probability of finding A times the probability of finding B. It's really simple. I'll show you in a second. If you don't put it back in the bag, then you have to do the probability of finding A, then the probability of finding B after A. You're thinking, what does that mean? Doesn't really make sense till we try an example. So let's try this one. Otto selects cards from a standard deck of 52 cards. If he randomly chooses one card, puts it back in the deck, and then selects another card without looking, what is the probability that he selected 2 queens? So here's the question. Did he replace it or did he not replace it? He replaced it, right? How did I know? It tells us that. He puts it back. So this is with replacement. Can you guys circle that in the notes at the top of this slide? So if it says with replacement or without, make sure we highlight the one that they're talking about. This one's with replacement. With replacement, our formula looks like this. Probability of A times the probability of B. So just write that down for a quick second. I don't ever like to leave random letters in there because A and B, that doesn't make any sense to me. So instead, we're going to do what are they really talking about in our problem. So the probability of picking a queen, and then the probability of picking a queen. See how I like to change the words so that they actually make sense for the problem that we're working on. So this is going to be a fraction times a fraction. On top is our desired. On the bottom is our entire. So let's start with entire. How many entire cards are in a deck? 52. Perfect. Now my desired outcome is a queen. How many queens are in there out of the 52 cards? What would you guys say? 4. Good job. So you have a 4 out of 52 chance of picking out a queen. Everybody okay with that idea? He's going to put whatever card he picked back into the pot. Now we're going to pick again. Let's try our second one. How many cards are we talking about? Well, 52. My desired outcome is a queen. How many queens are in the pot? 4. Great job. So what I'm wanting you guys to see is that when we replace it back in, you have the same probability the first time, the same probability the second time. Does that make sense? Because you're still picking from the same group of things. It's not changing. What if you did that 6 times? It will look the same 6 times. Same probability each time. So my final answer would be 16 on top, 2704 on the bottom, which reduces to 1 out of 169. So not that you're old enough to play poker, but if and when you are, you would have a 1 out of every 169 pulls of getting 2 queens in a row when you're pulling cards. Low probability, right? Doesn't happen very often that you're going to get 2 queens in a row. Happens, just not that often. Okay, you guys did great. Let's try another one. It says, Rochelle randomly pulls out 2 cards, one after the other, from a standard deck. What is the probability of getting a pair of aces? So let's think about this one. Does she replace the card or does she just pull 2 in a row? She just pulls 2 in a row. So guess what that means? Without replacement. She did not put her first card back. She pulled one, and then she pulled another one. Everybody okay with that idea? She pulled one, she pulled another one. So our formula is the probability of A times the probability of B after A. This is going back to the general definition. We're going to fill it in with real words in a minute. Because right now you're like, what does that mean? It's weird. So let's replace them with words. So I'm trying to get aces, right? So my first probability is, what's the probability of picking an ace? Okay, good. We'll move there in a second. This one you should know, it's just like the last one that we did, right? So our total goes on the bottom, our desired goes on top. So our total in our deck is 52. And how many aces are there in a deck? 4. Are we seeing a pattern? What if I ask you the probability of picking a 10? 4 out of 52. What's the probability of picking a 2? 4 out of 52. Okay? But now, my second part of my answer says, now I need to do the probability of B after A. So what that means is, what's the probability of picking an ace after you already got an ace? After getting an ace. Okay, we'll talk about that. Make sure you write that in there. It's important that we don't leave these random letters like A and B after A because that's so weird. We need to put real words in there. So probability of picking an ace, 4 out of 52. Now I have to do my probability of getting an ace after you've already pulled an ace. Okay, so stick with me for a second. You already have the first ace in your hand. Is everybody with me? How many aces are left in your deck? 3. Fabulous. Yes, 3. You have an ace in your hand. How many total cards are left in your pot? 81. Great job, yes. Perfect. That's what B after A means. It means there's going to be 1 less in the pile. Done. So that answer would be 12 out of 2652, which is 1 over 221.
So that was the same as the number.
It's not.
No, not the last problem, the one you did first. With the
Oh, yes. Yes.
So it's just a different thing.
Yes. So with replacement, do you guys see how our answers do vary though, right? If you're putting it back in the deck, you have a better chance of picking it than if you don't put it back in the deck. I'm just showing you with replacement and without replacement are going to give us different answers. Is everybody okay with why it was 3 out of 51? Okay, great job. These cards are kind of fun. Okay, we're going to skip this next one. We're going to move on to this one. A class consists of 12 boys and 14 girls. A teacher randomly pulls names from a hat. Did you guys ever have a teacher that would do that, like pull your names out of a thing for like answering questions in class and totally put you on the spot? And we have a teacher like that? I used to do that. If the teacher chooses one name and then another without replacement, what's the probability that 2 boys are selected? So first question, is it with replacement or without replacement? Without replacement, so let's underline that. Which, that was a good thing for you if you were in class, because otherwise technically the teacher could pull your name, put it back, and then pull your name again. That was never fun, right? It was good to know once you got picked for the day, you were sort of done for the day. I remember that. So what's without replacement? The probability of A times the probability of B after A. We're not going to leave it with these crazy weird variables in it. We're going to attach words to it. So what are we trying to have happen? We're trying to select a what? Probability of picking a boy. So I want the probability of picking a boy times the probability of picking a boy after a boy. Right? A second boy, so to speak. So we're going to have a fraction times a fraction. See how each time I already know pieces of my puzzle, and now I just have to count them up and add them in. My desired outcome over entire. Desired over entire, that's probability. I want to pick a boy. How many are we talking about? Look at the question. 12. 12 boys. Over my entire options. So I have 12 boys, 14 girls. What's my entire options here?
26.
Are we okay with how she found that? 26. 12 plus 14. Good job. So if you're a boy, 12 out of 26 times a boy is going to get picked. Okay, now pretend the teacher picked out the first name. She got a boy. Yes, it's what she wanted to have happen. So now what's the probability of picking a boy after you already have the first boy's name in your hand? How many boy options do I have left? 11. And how many total class students do I have left? 25. Perfect job. Do we see a pattern for when there's no replacement? Are you seeing a pattern here? What's the pattern? What's happening? Yeah, they're subtracting 1 because there's one less option out of one less option out of the total. So it's always just -1 on both of them. Great job. So by the time we reduce, well, we'll get 132 over 650, and that is 66 over 325. So keywords are replacement and without replacement. How'd we do? Okay? So far so good? Okay, great. The last thing on the list to kind of go over today are dependent versus independent events. So before I go to that slide, think about it. If you are an independent person, what is that saying about you? You stand alone. You do your own thing, right? If you're dependent on your parents, that means you rely on your parents for things. Are we okay with those definitions? Independent. You stand alone. You're like on your own. So if we're talking about, then here's your week 13 essential question, kind of middle of the road here. It says, give an example of an event that is mutually exclusive. So if you're at home watching this recording, this is the answer that you will put into the Dropbox. We have not covered this answer yet today. Give an example of an event that is mutually exclusive. I got the feeling that some students at home were just going to the end to see the essential questions, so I have it strategically hidden in the middle of the session this time. Don't cheat yourself. You need my help. Reading from online slides is not quite the same as having a teacher help you through problems. Okay, so let's try. Independent. And you don't have to write any of this down. It's already included in your notes, right? Because I don't like you taking class time to copy stuff down. Events are independent if the outcome of one event has no effect on the probability of the other. So everybody take your pencil. Let's circle no effect. So events are independent if one has no effect on the probability of another. And here's some examples. Landing heads after tossing a coin and rolling a 5 on a 6-sided die. They are not related. They are not the same. They are independent of each other. It doesn't matter if you get heads. It's not going to affect how you roll a dice. Does that make sense? They're two totally separate things. You picking a marble from a jar and then landing on heads when you toss the coin. Picking out of the jar, flipping a coin, not the same thing. They are independent. Choosing a 3 from a deck of cards, replacing it, and then choosing an ace as a second card. Even those are not dependent on each other because you're starting with the whole deck, and then what happens the second time? You're starting with the whole deck again. Does that make sense? And then rolling a 4 on a single-sided die, and then rolling a 1 on the second dice. Doesn't matter if you roll a 4 the first time, it's not going to affect what you roll the second time. So they're independent. Here's the difference. Dependent events do affect the probability. So let's underline that word or circle it. They do affect the probability. So this would be dependent. You drawing an ace from a deck of cards after a first card was drawn without replacement. If you don't replace it back in the deck, then it matters what you drew first. Does that make sense, the difference? If you don't replace the card, it matters what you drew first, because if you pick a 10 the first time, the probability of you picking a 10 the second time is very different, depending on if you got what you wanted or you didn't. And then they also put in selecting the best players for a sports team. That's dependent on, like say, the Yankees steal somebody in the draft. That's going to affect who the Dodgers make as their first choice, right? When you're allowed to pick and choose players, who gets picked first matters. They matter. They're dependent on each other. So this at the bottom is huge, and I added that for you on purpose. So without replacement is a dependent event, meaning when I don't put things back in the pile, that's when they get dependent on each other. If you pick 2 cards, your next card is going to depend on what you already picked. So when you don't have replacement, it makes it a dependent event. So there's a formula for independent and dependent events. We're going to try each of these. Independent events is just where you do your probability times your probability. This was your with replacement formula from just a minute ago. Dependent events is your without replacement formula. These are the same formulas we just did, except I want to show you one thing. They're going to write it differently now. Remember before we were saying P of A times P of B after A? Remember we were saying it like that? Now instead of all of those words, they're going to write it like this, B after A. It's just like a shortcut. That's all. We've already done this formula. It's just a shortcut for writing it. So let's try this one. There's an example at the bottom. What's the probability of getting 2 heads in a row when flipping a coin? Are these events independent or dependent? Meaning, the first time you flip, do you have the same probability the second time you flip?
Yeah.
Yeah, you do. So these are independent. Can we circle that word? Independent. So what formula am I using? The probability of my first one times the probability of my second one. Meaning, the probability of getting ahead times the probability of getting ahead. So, what is the probability of getting ahead? Let's think. What's my desired outcome? How many options are there to get ahead? 1. Out of how many total options on a coin? 2. So that's my P head. Now let's do P head again. Probability of getting ahead, how many heads are there? 1. How many total options do you have? 2. So my probability of getting ahead and then ahead right in a row is 1 out of 4. Straight across the top, straight across the bottom. Those are independent events, meaning doesn't matter what you flip the first time, the second time you could still flip either one with an equal amount of probability. This one I believe I gave you, did I leave all this in your notes right there? Okay, good. Whew. I try to make sure you don't have too much writing going on here. So let's read this together. Tori is picking cards from a standard deck without replacement. Without replacement. So before I go any further, circle without replacement in your notes. Remember that what that is that's probability of A times the probability of B after A. Or I could have done the line, B after A. What's the probability of picking 4 tens in a row? Are these events independent or dependent? Okay, you're not replacing them. Okay, you pick one, and then you're picking a new one, and then you're picking a new one, and then you're picking a new one. You're not replacing it. So these are dependent. It depends on what you get the first time. It's going to change your odds about your second pick. It's going to change your odds for the third pick. So dependent and without replacement, remember how on the bottom of that page I said those two go together? So whenever you guys see the words without replacement, that makes it dependent. That's telling us to use this formula. So let's look at what they wrote. What's my probability of picking 4 tens? First I have to do my probability of picking 1 10. So let's do that together. What's my probability of picking 1 10? So think about it. My desired over my entire. So our entire deck of cards we said had how many? 52. How many options do I have of picking a 10? 4. Everybody okay for my first one? Probability of picking a 10? Probability of picking a 10. Now I have to multiply that times. See, it got kind of long, which is why they put them underneath each other, but I would have had them side by side by side. If I had way more space, I'd have them going this way. So now my next one is going to be the probability of picking a 10 after you got a 10. So think about it. You already picked a 10. How many 10s would be left in your deck? 3. How many total cards would you have left? 51. You guys are doing great. So now my third fraction is the probability of picking a 10 after I've already gotten 2 10s, right? Now I've picked 2 10s already. So we were out of 3. Now how many 10s are left in my deck? 2. How many total cards are left? 50. Good job. And then my last one would be for picking my fourth 10. So the probability of picking my fourth 10 in a row. So how many 10s would be left? 1 out of 49. Good job. So remember, anytime you guys see the words without replacement, what does your formula look like? They're always decreasing fractions we talked about. They're always decreasing by 1 on both the top and the bottom. So that's our formula. Anytime you see without replacement or you see the word dependent, those mean the same thing. So if we can drill that in our head, without replacement, dependent, they mean the same thing. Your fractions are always going to be decreasing by 1 each time. So by the time I get my final crazy answer, it is a really small, I'm going to clear that out. It's like this really small decimal. Look at that percentage there. So what's the probability of you picking 4 10s in a row? I mean, you could tell me even without working it out. That's very unlikely. Would you agree with that? If I give you a deck and I fan them out and I said pick 4, you're not going to pick 10. You're not going to pick 4 10s. Like, that's a crazy low number. So that's just what this problem is showing you. Really, really small number. Yeah. Yep. I have one last kind that I'm going to do with you today. Oh, actually, let me just show you one thing on this one. The only difference on this problem, you guys, is says Ella's picking cards from a standard deck without replacement. So it's still that same decreasing formula. What's the probability of picking 5 of the same suit? So here's the question, though. See how she didn't tell you what suit you're going to pick? She didn't tell you. So your very first probability is your probability of picking any suit. If I fanned out cards for you and I said pick a suit, and you pick one, did you pick the right one?
Yeah.
Yeah, because I didn't tell you which one. So what's your very first probability? What are the chances that you're going to pick the suit? 1. Good job. So this one's just a little different in that your first fraction's not really a fraction because you're 100% guaranteed you're going to do what I'm asking you for. 100% guaranteed. What's the next one going to look like? The probability that the card is the same suit as the last one? It's actually 12 would be left in your deck. Because remember we said there's 13 in a suit, right? So how many would be left in that suit? 12. You already have 1 card in your hand, so how many total cards do we have left? 51. There you go. And since they want the first 5 cards, we would just do that till we got to the 5. 1, 2, 3, 4, 5. There you go. So I just wanted to show you that sometimes the very first number, it just depends on what they're asking you for. If it says pick any suit, well, you're going to pick that on your first card. What's the percentage? 100%. Whatever card you pick is going to be the right card. How many of that suit are left? 12. How many cards were left? 51. And we just go down by 1 from there. Okay, last idea. We're so close to being done. Mutually exclusive events are 2 events that cannot occur at the same time. So let me give you an example. Can you get a 1 and a 3 at the same time on a dice? No. They are mutually exclusive. They cannot happen at the same time. Can you get a heart and a black card at the same time? Picking one out? What color are hearts, though? Anybody know?
Red.
Hearts are red. So if you pick out one card, could it be a heart and a black at the same time? Nope. They're mutually exclusive. Can you get a head and a tail at the same time? Nope. So these are all mutually exclusive events. If I give you a bag of marbles and there's like all the colors in the rainbow, could you pick out a red and a blue at the same time? No. You just get to pick one, right? So those would be mutually exclusive events. So here's a couple other examples. These are not mutually exclusive. Picking a red or a peanut from a bag of mixed M&Ms varieties and colors. You could get a red and a peanut at the same time. They make red peanut M&Ms. Could you pick a 10 and a black at the same time? Yes. Could you pick a 2 and get an even number on a roll of the dice? Yeah, because 2 is an even number. So I'm just showing you that sometimes things are mutually exclusive, sometimes they are not mutually exclusive. So this is our last problem together today. So if it's mutually exclusive, we're going to do the probability plus the probability. And if it's not mutually exclusive, we have to do the probability of one, probability of the other, minus the probability of A after B. These are coming this week. You haven't done these yet, so I'm just doing a little prep work for you. You have not seen these yet at all. This is on Friday. So where's my example? Oh, here we go. Probability of getting a 2 or a 5 on a single roll of the dice. So can you get a 2 and a 5 at the same time, yes or no? No. So those are mutually exclusive, which would be the top one. So we're going to do probability of A, which means the probability of getting a 2, plus the probability of getting a 5. So we're talking about a dice here. What's the probability of rolling a 2? 1 out of 6. Are we okay with that? Talking about dice? 1 out of 6 total options. What's the probability of picking a 5? 1 out of 6. So 2 out of 6 would be your probability. Okay, you guys did great. This is what's coming at the end of the week. I'm just prepping you for it. You have not seen it yet. We'll jump into next week starting with a couple more of these examples because I don't want to overwhelm you, and that's a lot for one day. I always say I wish I didn't just have one day with you. I really feel math would be best if it was like 2 days direct instruction and then 3 days online. I don't know. I think that'd be a better blend. But it is what it is.
I think it was the whole week.
Or if it was the whole week. So just a reminder about your week 13 essential question. It was given somewhere during the session. So if you missed it, you do need to go back and watch the whole recording. I don't want students to fast forward through just to get the essential question because it's valuable practice time. Thanks, guys. Have a great